In this video, we are going to learn how to program our board. And for this, we will need software which is called MPLAB. So search for this software, click on this website, find the download section, and I'm using Windows, so I'm going to download this version. Click on this download link and wait until you download the software. Once you download this software, run the installer, and it should not be very difficult to install it. Click on Next, Accept, Next. Okay. If you like, you can enable everything, but we only need for our project this 8-bit microcontroller. Click on Next and wait. Install drivers. Uncheck this and finish. Once you install MPLAB, we will also need a compiler, and these two pages, they should automatically open after you install MPLAB. If they do not open, you can simply just search for XC8 compiler MPLAB and you should be able to find it. So on this page, scroll down, find the download section, click on compiler downloads, and we need XC8 compiler. So just left click here to download the file or the software. Once you download the compiler, install it. Next. Accept. Next. Free. Next. Next. This can be very useful, so check it, because it can help MPLAB to find the XC8 compiler. Click on Next. Next. And wait. Click on Next. And finish. Once you install everything, you can start the software. So I'm going to click on this Windows button. I'm going to find Microchip and start this software, MPLAB X IDE. In the next step, we would like to install something what is called MPLAB Code Configurator. Maybe you remember it when we installed MPLAB, two websites opened, and one of them was the compiler, and the second website is the Code Configurator. And there are more ways how you can install this configurator. We are going to do it directly from MPLAB. Once you open MPLAB, click on Tools, Plugins, click on Available Plugins, and in this list, find the MPLAB Code Configurator. check this, click on install, click on next, accept, install, and we need to wait. This code configurator is super useful. A little bit later you will see how we will use it. Once it is installed, you will need to restart the MPLAB. So click on finish and wait. Once the MPLAB is back, once the software is open again, take the debugger, PickKit4 debugger, and connect it to your computer USB. You should see something like this. And sometimes, especially if you are using completely new debugger, it may take some time. So just be patient and wait. Once the debugger is correctly installed, you should see it in devices and printers. So just search for control panel, go there, and inside of devices and printers, when I scroll down, here is the MPLAB PickKit debugger. Okay, so once all the drivers are correctly installed, you should see it here. Now, go back to MPLAB, and we are going to create a new project. Click on File, New Project, select Microchip Embedded, Standalone Project, click on Next. Here we need to select the microcontroller what we are using. So go into our schematic, select the microcontroller, copy the manufacturer part number, select Ctrl+C, go back into MPLAB, Ctrl+V, and just delete the last characters, maybe like this, okay? So here is the microcontroller in this list. So select it, and in the tool, you should see in this drop-down list, you should see your debugger. If you don't see it, it means debugger is not probably correctly installed. You should see it here. You still may be able to select this debugger if you just click here and you can select it from this list. But you still should see it even when this is not checked, because if you don't see it, there is something wrong. Select it from this list, click on Next. Okay, just Next. We don't have any special header between the debugger and the board, so none is fine. Next. Now you can see our MPLAB automatically found the compiler what we installed, and it is because we checked the path when we were installing the compiler. So I'm going to select it, click on the Next, and select the location of the project. I'm going to put it here, and I'm going to call it Tiny Simple. Set as main project. Use project location as the project folder. Okay, we can do that. And click on Finish. Before we actually start writing this software, there are few things what we may want to check. So first, go to Tools, click on Options, click on Embedded, and click on this Build Tools. Here in this list, you should see the XC8 compiler, and it should be selected. Okay, this is very important. If you don't see it here, click on this Add button, and find where the compiler was installed. It will be probably somewhere here, and add the location here. Also, if you don't see this compiler in this list, you probably have problems to create new project because then there will be the compiler will not be listed in the list of compilers. And if you add the compiler here, and then when you try to create the new project, it should work. Okay, so in case you are having any problems with compiler, double check it inside of these options, embedded build tools. Very important. The second thing what we would like to double check are the settings of our debugger. So right click on this project, right click here, select properties, left click on PickKit 4, and from this list select tool options. We don't want to use high voltage programming mode, so left click here and select low voltage programming mode. Also from this list select power, and this needs to be unchecked. Okay, we don't want the debugger to power our board, so be sure this is unchecked, and if everything seems to be correct, click on OK button. Also, I would like to say MPLAB, it sometimes keep crashing and freezing. So in case you are having any problems, or if you see MPLAB is behaving some kind of weird way, try to close the software and start it again. Very often it may help. And now we are ready to start doing this software. Right now, if you have a look inside of the source files, they are empty. There is nothing. And if you don't know how to write software, don't worry. We are not going to start from scratch. We are going to have a little bit of help. And to start with our software, go to Tools, Embedded, and we are going to use this MPLAB code configurator. Left click. Once the MCC or MPLAB code configurator is loaded, the very first thing what we would like to do is to set the correct package. So from this list, I'm going to select, do you remember which one is ours? SSOP20. If you go into our schematic, you can actually see it here, okay? SSOP20. And now here you can see the pins of our microcontroller. And here in this table, you will see how they are assigned to what peripherals and what features and functions. Why we would like to use this MCC configurator, do you know? You don't have to use it. What you can do, instead, you can open datasheet and then based on the peripherals, what you would like to use, you find the specific registers, what you need to set, then you would read what is the function of every single bit in these registers, and you would set them correctly. Sometimes, if you would have to do it this way, it can be a lot of work. It can be like super time consuming. Sometimes it's like very difficult to measure some of the settings, if you set it correctly or if it's wrong, or sometimes it just doesn't work and you can find out why it doesn't work, and it's because you forgot to set one bit somewhere in the register of the microcontroller. You can spend days, sometimes even weeks, trying to set microcontroller registers correctly. If you use this MCC configurator, it's going to be much more simple. Basically, here are some forms and some features which based on what you need for your application, you just select these features, you set these forms, and the MCC will automatically calculate what are the correct values for the registers, what you need to set. And MCC code configurator also generates some basic functions which you can very simply just call from your code and use them. So it's not going to only save you time from setting up the registers and bits inside of the registers. It's going to also save you some time from writing the very low and basic functions. You will see a little bit later, once we set up this MCC and once we generate this code, you will see what everything this code configurator can set and what it will generate. The very first thing what we are going to set is this system module internal oscillator. So we would like to use internal oscillator because we don't have any external crystals or oscillators, and we would like to run our microcontroller at highest possible frequency for testing. So I'm going to enable PLL. It means when we enable PLL, we can multiply by 4 the frequency what we will select here. Okay, so internal clock 8 MHz multiplied by 4 is 32 MHz the system clock. Also notice the watchdog is disabled. We are going to leave this, and the programming, the low voltage programming mode is enabled because this is checked, and this is exactly what we set in our debugger settings. I'm going to move this a little bit down because we don't really need to see what is here. This is a little bit more important. And okay, these are the settings for the system module. What now? Open schematic. So when I open our schematic, here you can see what we would like to do with our microcontroller, and we would like to control our RGB LED. So in the MCC configurator, we would like to enable PWM feature for RC3, RC5, and RC6 pins. We need to open datasheet of our microcontroller, left click on the symbol of the microcontroller, left click on view datasheet, open datasheet, scroll down, and we would like to find the table with pin and feature descriptions. So for 20 pin footprint, that's what we have. We would like to see what CCP modules we need to use for RC3, RC5, and RC6 pins. So remember this is very important. We will need to use CCP2, CCP1, and CCP4. Go back to MPLAB, and we are interested about these CCP and eCCP modules. These are the modules which can give the PWM feature or functionality to the pins what we are using to control the LEDs. So click on this plus symbol on eCCP1 module. We added the module into our project resources. We would like to use it in PWM mode, and notice this warning. To be able to use this ECCP1 module, we have to set a timer first. And by default, looks like they are suggesting this timer 2. So inside of this timer, find timer 2, click on plus. Okay, now in project resources, we also have the timer, and we would like to set this timer to period 320 microseconds, something like this, okay? So just set the prescaler to 1 to 64, add 0 here, press enter, and then you will see the period will be 320 microseconds. Actually, you can use any period you like. This is something what I just used for testing. It may depend on what kind of LED, for example, you are using, or what kind of frequency you can use in your project. If you are not sure, you can use exactly same numbers what I'm putting here. Okay, now the timer 2 is set up correctly. We can go back to ECCP1 module. You can see the default duty cycle is set to 50%, and everything here is correct. Perfect. We also would like to set the ECCP2 module. Click on plus. We would like to use it in PWM mode, and everything else is set correctly. Double check the timer selection, and we would like to also use CCP4 module. We would like to use it in PWM mode, and initial duty cycle set it to 50%. Perfect. What we also would like to do, we would like to go inside of this pin manager window, and we would like to double check if the assignment for the pins of our microcontroller is correct. From this table, you can very nicely see if we have connected our schematic correctly. So basically, in this table, you can see that PWM output from CCP4 module is going to be on pin number 8 of our microcontroller. Here is pin number 8, or otherwise it is called RC6 pin. So let's go into our schematic and let's see if it's connected correctly. RC6 pin number 8 is controlling the brightness of the green LED on our board. Perfect. Let's check the other one. The output from the ECCP1 module is on the pin number 5, or RC5. If we go into our schematic, RC5 or pin number 5 is controlling the brightness of the blue LED. Yes. And the last one, the PWM output from ECCP2 module is connected to pin number 7 or RC3 pin. And in our schematic, RC3 or pin number 7 is controlling the brightness of the red LED. So our schematic is connected correctly, and we can use PWM signals to control the brightness of these LEDs. Notice some of these outputs, they can be actually assigned to different pins. So for example, the PWM output from this ECCP2 module can be also on this pin number 2. If it's green, it is on pin number 2, or RA5 pin. But this is not what is connected in our schematic. in our schematic it is connected to this pin, so we have to left click here and this has to be green, okay? Be sure you configured this table based on your schematic. Also notice here are some other options what you can maybe select, but in our application we are not using these pins of these modules, okay? If you would like to know more how these pins can be used for these modules, read datasheet. But the PWM output, what we need for our board is on these PA pins. So it is on P1A and P2A pin. Here are the PWM outputs, what we need from these ECCP modules. Okay, so that's perfect. We designed our schematic correctly. When you will be checking the setup of the pins, you also may want to click here in System Pin Module and have a look what are these settings here. Sometimes you may want to enable like pull-up resistors, or you may want to set some of the outputs as open drain. You can do it in this table. And what I'm going to do, I'm going to uncheck this analog because our RC6 pin is going to be just standard output. There is one more very useful thing what we can use for our simple example. I'm going to click on this foundation services and I'm going to add delay. So when we will be creating software, we can very simply set, for example, how long the LED should be on or off. So I'm going to click on this plus, and here I'm going to set the delay between two instructions. Perfect. Now we are ready to generate the MCC output. By the way, when we selected this example, it means that when MCC generate the code, in this code will be an example how we can use this delay feature or delay function. I will show you a little bit later how it looks. Let's do it. Let's click on this generate button and let's see what will happen. Left click. It's done. Looks like there are no errors. We can go back into our project, click here, and now you can see inside of these source files, now there are actually some files. Everything this was generated by MCC automatically. The main C, double click here, this main.c file is the file where we are going to write our software. And these files are the files which are going to set up the registers for the peripherals, what we are using. These are the files which are going to help us to use these peripherals. There are some simple functions which we can use. And also here is the example of the delay feature. Here is the example which will explain how you can use it if you would like to. Finally, we are ready to write some code. So double click on main.c, scroll down, and our code is going to be inside of this while. Our very first code is going to look like this. First, we are going to set duty cycle to 100% for all LEDs. So basically what this means? It means we are going to switch on RGB LED. So it means there will be white color. And then we will wait for 1 second. And after 1 second, we will change the duty cycle to 0%. It means we will turn off the LED. And then we will wait for 1 second. Okay? This is going to be our very simple initial code. Of course, it's not going to work like this. We need to put there the real functions, what we need to call. What kind of functions? The functions which are going to change the duty cycle of the LEDs and the delay function. To figure out how to use the delay function is going to be super simple because we have this example here. So I'm going to open it. And when you have a closer look on this example, you can see everything what we have to use is just call this delay microseconds or delay milliseconds function. So ideally, maybe we would like to use this one, delay milliseconds. I'm going to copy this, Control C, go into our main file, and here I'm going to Control V, and I'm going to change this to 1000. 1000 milliseconds is 1 second. I'm going to copy this, Control C, and I'm going to put it also down here. We don't have any examples about how to use PWM modules, but we have these header files. Go inside, open, for example, this PWM4 header file, just double click. And inside of header files, you will find all the functions which you can use with specific module. When we have a look inside of this PWM header file, when I scroll down, you will see there is, for example, this PWM4 initialize function. And when I continue scrolling, there is also this PWM4 load duty value function. When I go at the end of the file, there are no other functions. But this is okay, because this is the function what we need. This is the function which is going to help us to set the duty cycle of our PWM output. If you like, there is also some short description about the function load 16-pin duty cycle. But what is more interesting is this example, which will tell you how you can use this function, don't worry about this one, PWM4 initialize. We don't have to run this function because this one is automatically included in the initialization process. So if we go into our main C file, and when I go at the beginning of the main function, here you can see this system initialize function. This was automatically created by MCC, and this function runs all the initialize functions for each module which we are using. Okay, so that's the reason why we don't have to run this one, PWM4 initialize, because it is automatically included in this system initialize function. Okay, I'm going to copy, I'm going back to PWM4 header file. I'm going to copy this example, which is here. Control C. I go back into our main file, and we would like to use it here. Control V. So this function is going to load the duty cycle, which is specified here. I'm going to double check what is the variable type for this duty cycle. So in PWM4 header file, this is what we would like to see. I'm going to copy it, Control C. I will go back to main C. I will put it here like this, and I'm going to put there this. So do you know what we just did? We specified the duty cycle variable. We use the specific type, which is basically required in this function, and this function PWM for load duty value is going to set the duty cycle of PWM4 module. Everything what we have to do now is, do you know what we are missing? We need to set this duty cycle variable, so I'm going to copy it, Ctrl C, and I'm going to set it to 100. No, that's not right. Okay, this value which is inside of this load duty function, it's not in percentage. If we go back here, you will see it just says it's 16-bit duty cycle number. And this number you can very easily get from the MCC configurator. If we go into the CCP4, when I open it, then this is the value what we would like to put there. For 100%, if I put here 100, enter, we would like to maybe use 159 value for the function. And from my experience, I know we actually need to use 160, okay? Then the duty cycle will be 100%, because this is just approximate number. It's hard to calculate the exact numbers. So I'm going back into main C, and I'm going to set this to 160. Okay, you understand everything what we did? Based on the header files, we figure out what kind of functions we can use to control these specific modules. And inside of the PWM header file, we found out that the function what we would like to use is this load duty function. And the number what we have to use for this function, we got the value from this MCC, and it was calculated approximately when we set the duty cycle here and presented this is the value. So for example, if you would like to get like 10% duty cycle, you would use value 15, okay? For, I don't know, 70%, you would use 111. Little bit later, we can try different values and measure them so you can see how it looks, how the real signal looks. Okay, in the main C, we would like to do exactly same for all the colors. So we have to do this for all the modules, not only for PWM4 module. It means, what do we need to do? We need to go, for example, inside of this other header file, find the function which is going to set the duty cycle. This one, I'm going to copy it, Ctrl C, go back to main. I'm going to put it here, Ctrl V, and open also this EPWM1 header file, and copy this one, Ctrl C, go into main file, Ctrl V. Okay, now copy everything, paste it here, and here we would like to set the duty cycle to 0. Okay, I'm curious what is going to happen. I really hope we set up everything correctly, and if yes, then our LED should be switching on and off in 1 second interval. Before we actually connect our board, first let's try to compile this code if there are no errors. And to compile your project, simply click here, left click. compilation has finished and there are no errors. If there are any errors, you need to go back to your code and double check maybe what you have different comparing to our video, okay? So once there are no errors when you try to build your project, you can connect your board. We will need 2 USB cables and a USB hub which is connected to our PC, debugger, and our board. I'm going to use this USB cable to connect debugger to our PC, so I'm going to connect it like this. Next, we would like to connect our board to our debugger and be super careful where pin 1 is located. So on our board, pin 1 is located here, okay? And on the debugger, the pin 1 is marked with this triangle, so it is located here. And this is basically the way how we need to plug in our board into debugger. Only what is missing is to connect power to our board. So I'm going to take this second USB cable, I'm going to plug it in, and what is going to happen when I connect this cable to our board? Do you know? The green power LED should be on, and because there is no firmware, basically nothing should happen. Sometimes LED may flash a little bit or something, but basically everything should be off, just a green LED, and that's okay. That's what we are expecting. So I'm going to plug in this. Okay, green LED and nothing else. This is fine, this is perfect. And now, this is the moment of the truth. This is the moment we have been waiting for. This is the moment we will find out if our board is working. To upload our firmware on our board, simply just press this play button. What is going to happen when I press this play button? What we should expect here? We should see this RGB LED to switch on. What color will be used and what brightness will be used on this LED? We switch on the red, green and blue color on full brightness, and it means when these three colors will mix together, they will create the white light. So this LED should switch on, the light should be white, it should stay on for 1 second, then it should turn off for 1 second, and then this should repeat. Fingers crossed. Let's see what is going to happen. I'm going to press this triangle, left click. Yes, it's working. If your board is working, then well done. Fantastic job. Next, we are going to double check if what we think is our code doing, if this is really happening on our board. So we are going to do some measurements, and also we are going to play a little bit with the code. It will help you to understand a little bit more of what we have done, and possibly, for example, if you would like to modify something, then this can help you to understand what you should change and how you can do it. Open schematic, and we would like to measure, for example, this signal which controls the red LED. So select this signal, left click, go to Tools, Cross Probe, and let's see where this signal is on our board. Left click. Here it is. Okay, so when we have a look on our board, real board, then This is the path where we would like to measure this signal. This is my oscilloscope. I'm going to put the probe on the path. Okay, I'm going to stop it, and let's have a closer look what we have there. This is the signal which controls our red LED. This part of the signal will switch on our LED. This is the signal which will switch off our LED. Notice that when the LED is on, this signal is always high. And this is because we set the duty cycle to be 100%. When we will change the duty cycle, you will see how this will change. Okay? At this moment, what we would like to do with this signal is we would like to double check if our LED is switched on for 1 second and if our LED is switched off for 1 second. So we would like to measure what is the time between this rising edge and this falling edge, and also between this falling edge and this rising edge. Let's do it. I'm going to enable the cursors, and I'm going to move the first one on the beginning of our signal, on this rising edge, and I'm going to move the other one at the falling edge. This is the time when our LED is switched on, and you can see it is 1 second. Perfect. I'm going to move this one, and we are going to measure the time, how long the LED is switched off, and also it should be 1 second. 1 second. Perfect. Let's go back to MPLAB, and we are going to change this duty cycle from 100% to 10%. Do you remember how to do it? Go to MCC, double-click on CCP4 module, and in this duty cycle, change this to 10. Enter. This is the number what we have to use, 15. Go back to Projects, double-click on Main File, and here, change this to 15. To compile and upload this new updated software on our board, just use the play button, okay? Play button will automatically compile and flash the new software. So left click and watch what is going to happen on our LED. The brightness should be lower. Can you see the difference? The brightness is now much lower, and it's lower because we use this special PWM feature. Let's have a look how this feature changed our signal. Here is my oscilloscope, and we are going to measure the same signal as what we measured before. So I'm going to place the probe here, and what's this? Notice when the LED is on, suddenly the signal is not like always high. Something is happening here. And when we zoom in, you will notice basically the LED is switched on for some short time, and then it is switched off. Switch on, switch off. And this signal, what we can see here, that's what the PWM feature is doing. And what we can do, I can zoom in maybe like this. I can stop this and we can do some measurements. What can we measure here? We can measure the frequency of the pulses, or basically the time between rising edges of the pulses, and also we can measure duration of the pulse, so when the pulse stay high. What numbers we should get? Do you know? The numbers what we set in our software. When we go into MCC, and when I double click on this CCP4 module, these are the settings what we should see. So the frequency between the pulses should be 3.125 kHz, or when we will measure the time between the rising edge of the pulses, we should measure 320 microseconds. Remember this, okay? 320 microseconds. And for how long the pulse should stay high? For 10%, how much is 10% from 320 microseconds? 32 microseconds, okay? So we should measure 32 microseconds the pulse width, and we should measure 320 microseconds between the pulses. Let's have a look. In these measurements, you can see the frequency of these pulses is 3.13 kHz, and we set 3.125, so this is okay. The period between these pulses should be 320 microseconds, and you can see we measured 319.2 microseconds. And when I enable cursors, and when we measure the width of this pulse, we should get 32 microseconds. 32 microseconds. If you would like to change something in these settings, then go to MPLAB, and for example, if you would like to change the frequency, double click on our timer and you can change the settings here, okay? This is the place where we set the period 320 microseconds. For your LED or for your application, maybe you can use different numbers. For this tutorial, I just use 320 microseconds. There is no like any special reason for this. You can use anything what works for you. If you would like to then calculate the duty cycle, then you can, for example, go to specific CCP module, and if you change the number here, you will get the value which you will then use here in your main code. So right now it is not 100%, so I'm going to maybe delete this, because then it will be more accurate. Okay, that's everything about PWM, and maybe we could also try something else. For example, what we could do, we could find out which of these PWM functions is what color. So I'm going to change the duty cycle to 100%. I'm going to use value 160, and I'm going to comment out two of these lines. Let's update the firmware and let's see what color we will see. Left click. I can switch off the lights so you can see it better, and it's the green color, so I'm going to put here a note, green. I'm going to comment out this one, uncomment this, and compile. This is the red one. And the last one should be the blue one. Compile and upload. Perfect. Now, if you would like to do some effects, you will know how to control each individual LED. Of course, what you can do, you can also mix not only different colors together, you can mix also different intensities of each color. So you can create all the kind of different effects with your LED. We learned these basics. Now we would like to do something a little bit more complicated. We would like to learn how to use I2C bus so we can talk to our accelerometer. And again, it's not going to be so difficult because we can use this MCC and it is going to help us a lot. Click on this MCC tab, and to support I2C, we would like to add this MSSP module. And there are actually two modules. So which one we should use? Depends on our schematic. If we go into our schematic, and when I zoom in, you can see we connected I2C1 bus. This I2C1 bus is connected to RB4 and RB6 pins. If you go into datasheet, and when you check the SSP module, then you can see RB4 is connected to SDA1, so I2C1 bus, and RB6 is connected to SCL1, so I2C1 bus. This means we would like to use MSSP1 module. Click on plus, and everything what we have to do here is just to change the serial protocol to I2C. Go to Pin Manager, and we are going to double check this table with our schematic. So MSSP1 SDA1 signal should be in our schematic connected to RB4. If we open schematic, SDA is connected to RB4, and the clock signal is connected to RB6, and in our schematic the clock signal is connected to RB6. Perfect. This means this pin configuration is correct, and it is exactly as we have it designed in our schematic. Now, we have some basic support for I2C, but it still can be quite a lot of work to actually talk to our accelerometer. And to make it easier, we are going to use this foundation service I2C Simple. If you would like to know what exactly this is doing, you can click on this help button, and you can see when we use this foundation service, we will get access to these functions. And this is exactly what will make it super easy to talk to our accelerometer. We simply can use, for example, this function. We just put here the address, I2C address of our accelerometer. We will just say what register we would like to write to, and here we will put the data which we would like to write. So this is like super helpful. If we don't have this foundation service for I2C, we would have to write these functions by ourselves. But because they already did it, we can use it, and it's going to save us a lot of time. So simply just press this plus button, and add the I2C simple service here. If you like, you can also generate an example how to use this I2C foundation service to talk to EEPROM memory, but we don't need this example, so I'm just going to leave here none and press generate. There are no errors, so go back to our project, open main file, and before we start writing something, we would like to see the datasheet of the accelerometer. Go to schematic, select accelerometer, click on view datasheet, and open datasheet. Probably the simplest way how to check an I2C device is to read its ID. And to read this accelerometer ID, we will need 3 numbers. We will need to know the I2C address of this accelerometer. We will need to know what is the address of the register where this ID is located, and also we will need to know the ID. We need to know if the number what we read, if that's the correct number, if that's the expected number, what should be there. So let's find these 3 numbers in this datasheet. We would like to see content of this datasheet, so I'm going to click here. Now in digital interface, click on I2C operation. In this table, you can see the I2C address of this accelerometer, and the address depends on one of the pins, address path pin, how it is connected. If we go into our schematic, and when I zoom in, you can see this address pin is connected to ground. So if we have a look inside of this table, when address path is connected to ground, the address of our chip is 0x0e. Okay, so go into our code, and at the top of our file, up here, write something like this. Define the address of our accelerometer is going to be E. This line is something what will tell this software that everywhere in our code where we use this word, this software will automatically replace it then with this E number. We use this line because it will make it easier to read our code. Instead of using E in our code, we will immediately know, this is the address of our accelerometer. And also, in case in future you would like to change this number, it is much easier because it is only in one place. Okay, so theoretically you don't have to use this number, or you don't have to use this line of the code. You could directly use this E in the commands what we are going to use next, but this is this makes it easier to read your code, and also it will keep this number in one place in case you need to change it in future. Let's go back to our datasheet, and we would like to find the address of the register where the device ID is located. Click on these embedded registers, and this is the register Who Am I. This is the ID register, and you can see the address of this register is F, or 0x0F in hexa. When I click on this register, left click here, you can see the default value of this register should be 0x35. Okay, we know all the numbers, what we need. Go to MPLAB, and inside of these header files, MCC generated files examples, you will find this I2C1 master example header file. Open it, and inside of this file there are all the functions which we can use with our I2C module. And the function what we need is this one. Basically, we would like to read 1 byte from the I2C device on this address and from this register. Okay, so this is exactly what we need. I'm going to copy it, Ctrl+C, and I'm going to place it inside of our main file. I'm going to place it maybe somewhere here. We are going to make a few adjustments. So first I'm going to create new variable, Ctrl+C, Ctrl+V. I'm going to call it data, and the results of this function is going to be assigned to this new variable like this. Now go up, copy the address of our device. I'm going to put it here, and I'm going to create I'm going to also define the register address like this, and I think it was F. Yeah, 0x0F. So I'm going to put it here, copy this, and place it here. We can use red and green LED to indicate if we were able to read the accelerometer. So I'm going to place here very simple condition like if data are what we should read. Do you remember? The default value is 0x35. So if data are 0x35, it means we are able to communicate with our accelerometer. So let's light up the green LED, use full brightness, otherwise there is something wrong. So switch on the red LED at full brightness and stay on for 3 seconds so we can see it. Don't forget, by default, when we initialize PWM, we will set the output to 50% duty cycle. So to be able to see this, we need to switch off all the LEDs first. So I'm going to copy this, and I'm going to place it here. Also, we are using this function from this example header file, and this one is not by default included in our main project. So what we would like to do, we would like to include this example header file. We would like to include it up here, write this line here. Okay, now our main file will be able to recognize this function what we are using here. I think we are ready, or at least I hope we are ready. Let's see what will happen when we compile and when we run this. Watch the LED. If we are able to communicate with the accelerometer, then when we upload the new firmware, the LED should be green, and it should stay green for 3 seconds. If it will be red, there is something wrong. So I'm going to press this play button, left click, and I'm really curious. Green! Yes! 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 If on your board you can see the green light, well done. If it doesn't work, if your LED shows red, then you may need to do some debugging. And the very first thing what you may want to check is how well the accelerometer chip is soldered down, okay? Because this was my case in my test boards. Some of them were soldered badly, and then microcontroller was not able to communicate with the accelerometer. So what you may want to do is maybe remove the chip and solder it down again, or maybe try different board. I'm going to show you how you can, for example, measure this I2C bus and what you should see there. Place the probes on the SDA and SCL test points. So I'm going to place this one here and this one here. Now, set your scope to single mode like this, go to MPLAB and press play button, left click. Watch what is going to happen on your oscilloscope. I don't want to go like too much into I2C communication. You can just search for more details, but what we see here is in this first transfer we are sending the device I2C address. Then in this second transfer, which is here, we are sending the register number, what we would like to read. Then we are sending again the chip I2C address, and then this is the number of what we are reading from the accelerometer. Okay, so this is like super simple explanation. What you should see if the communication with the accelerometer is correct. This is the example of reading the device ID from the accelerometer. Once your accelerometer is working, you can have some fun and you can play with this code. For example, I'm going to delete this while and I'm going to replace it with something like this. Okay, so we are going to initialize the accelerometer. Here are some values what we need to change in the registers, and then basically what we will do, we will read X, Y, and Z values from the accelerometer, and based on these values we will light up the LEDs. And when you compile this code, this is what is going to happen. I'm going to press this play button, I'm going to compile it, load it on our board, and this is how it should work. Based on the orientation of your board, the color of the LED should be changing. So for example, now you can see it is green, but if I rotate the board like this, see, it's red. When I put it back, it's green. And when I rotate the board like this, then it's blue. Okay, so this is what the very short code is doing. Now, what you may find super useful is to learn how to debug your software. So basically, what you can do, you can actually stop this software and you can have a look what are the values inside of these variables. So basically, let's say we would like to stop our software here on this line, and then we would like to check these X, Y, and Z values which we read from the accelerometer. To stop the software on this line, we need to place their breakpoint. And It's very simple, just left click on this bar which is here and on the line where you would like to stop the software. Now, instead of using this play button, this time we are going to use this button, debug main project. Okay, so just left click here and now wait until the software will compile, it will flash to our board, and then it will stop on this line. See, now the software stopped here because it is green, and now when I hover cursor over data X, I can actually see what data the accelerometer sent to our software. It is 0xDA, okay? Data Y are 0x9 and data Z are 0x33. This debugging can be like super useful, okay, if you would like to learn more. Again, search on internet, but basically this is something what I wanted to mention in this video. There is something else what I would like to show you in this video. We would like to learn how to work with interrupts, because it can be super useful. And maybe you remember this user button from our schematic. We could write some code which will be only called when we press this button. Okay, so let's do it. Let's learn how to work with interrupts, how to create this special function which will only be called when something will happen. Go back to MPLAB. We can stop debugging our board, so I'm going to press this red stop button. Go to MCC, and what now? Go to Pin Manager. I'm going to move this a little bit up because we would like to see it. And I'm going to move this a little bit down because we are going to use these modules. In the Pin Manager table, we would like to set the pin where button is connected. We would like to set it as input. So in schematic, we are going to double check where this is connected. RB7, pin number 10. Go back to MPLAB. Pin number 10, RB7. Set this pin as input. Just left click here. In Project Resources, System, go to Pin Module, left click, find RB7 pin, and for this pin we would like to enable internal pull-up resistor. So check this. Why we would like to enable this pull-up resistor, do you know? If you have a look on our schematic, when we set this RB7 pin as an input, then basically there is no really specified value on this input. This input would be floating. That's the reason why we are enabling the internal pull-up resistor. When we enable this internal pull-up resistor, then by default on this input there will be a signal in high, and then when we press this button, the level on this signal will change to low. Go back to MPLAB, and when you enable this internal pull-up resistor, notice there is this warning. Please enable NWPUEN bit from register view. So don't forget, you need to go here inside these registers, left click, and in these registers find this NWPUEN register or option and enable it. Okay. Now go back to Easy Setup, and also we would like to enable the interrupt for this pin, and we will do it here in this column. So from this drop down list, select negative, and it means we just enabled interrupt, which will happen when the signal level on this RB7 pin will be changing from high to low. You can double check if this interrupt was enabled when you click on this interrupt module, and when you scroll down in this table, pin module enabled checkbox should be checked. Okay, this means we enabled interrupt for this RB7 pin. Click on generate. There are no errors, so go back to our project, open main, and before we start writing the code to support the interrupt, we would like to check if our hardware is working correctly and if the internal pull-up was set correctly. We are going to measure the level on the button signal, so I'm going to place probe here on our button test point, and you can see at this moment the level is low. So when we go back to MPLAB and when we compile this new firmware, we should see the internal pull-up being enabled, so we should see this signal to go high. Left click here and let's see what will happen. Perfect, this is working. When we go back and when I press the push button, we should see the signal going low. Okay, perfect. So hardware is working correctly. Now let's write the software for our interrupt. I would like to keep this video simple, so we are not going to talk about this interrupt into details. If you would like to know more, you can, for example, have a look inside of this interrupt manager header file. But basically, if you would like to use interrupts in your project, this is what you need to do. Go up, and after system initialization, put there something like this. Set interrupt handler. So for our GPIO pin, we would like to set interrupt handler, which will tell our software what function should be called when we press the button. And this is the function what we still need to create. So I'm going to scroll down in this code, and usually these interrupt handlers are at the end of the main file. So I'm going to put it here. You can see it's called button interrupt. That's exactly the name what we used here. And inside of this function is what should happen when we press the button. At this moment, it's something super simple. You can see basically when we press the button, our LED should get white for 3 seconds. This is not maybe the best example what you should use in interrupt functions because it takes a long time to execute this, but this is just an example, okay? Now, what we need to do, we also need to declare this function because it is defined at the end of our file, and we would like to be able to use it in the code before. So I'm going to declare the function up here. And this is how you do it. And also, once everything is set up, we would like to enable the interrupt. So we need to uncomment this line and also this line. And that's it. If we set everything correctly, then it should work. Let's try it. My MPLAB just completely crashed. I had to close the software, I had to disconnect the debugger and our board, and I had to connect and start everything again. And I hope now everything is ready to try our code. So I'm going to press this play button to compile and flash the software. Left click. Okay, green LED, it means microcontroller can communicate with accelerometer. Our original software is still working. You can see this is the blue LED, this is the green one, and the red one. And the new feature, what we just created, is when we press this button, the color of the LED should be white, full brightness for 3 seconds. So let's try it. Yes, the interrupt is working perfectly fine. And that's it. That's everything for this tutorial. Or is it? If you like this tutorial, and if you would like to maybe see more videos, leave comments, okay? Let me know what we could do. We could actually go one step further, and we could maybe design whole product together. Because the main goal why I designed this board is to place it inside of this wand, and then you will see. You can guess what is going to happen with this wand. But I could create another video where we could learn how to use this Fusion 360, how to create enclosure for our board, so how to create this wand. We could then see how to 3D print this wand and maybe how to debug the wand. You can see I have cables going out of this, so I can do some debugging and, for example, read the accelerometer values and all the kind of things. What maybe if you would like to see how to do it, leave comments and I can create some additional videos for this tutorial. I would like to thank you very much for following this tutorial, and if it helped you, I'm very happy. So that's it. Thank you very much for watching, and see you in some other videos. Bye.